Hey, this is Dr. B, and let's have a look at nuclear imaging and radiotherapy. We're going to look at five techniques here. The first three being imaging techniques, and the last two being therapy techniques that all involve unstable nuclei. The first one we're going to look at is SPECT scanning. SPECT standing for single photon emission computer tomography. This is in some ways similar to the barium swallow test that's far more common, you might have heard of, where a radioactive substance is ingested and it lights up different parts of your body. We'll take a look at PET scanning, which is positron emission tomography. This is oftentimes used for cancer investigations, imaging thereof. MRI is something almost everybody's heard of, magnetic resonance imaging. This does not involve the use of a radionuclide, but it does involve the relaxation of nuclei as they're spinning, so it's similar in some ways, much safer. Radiotherapy directly by targeting a radioactive substance at a different part in the body and using the energy that's involved in order to eradicate a problem. And here's an experimental technique, targeted alpha therapy, which has great promise for specific targeting of multiple carcinogenic locations simultaneously. Okay, so the first three are imaging techniques. Let's have a look at them. A SPECT study would involve a common radionuclide, something that's unstable. In this case, it could be technetium-99. These can form nice complexes that tend to go to certain parts of the human body. Here's a substance known as Ceratec. Notice the technetium-99 right in the center. For this organometallic substance, this would tend to go to the brain. Here's another one known as MyoView, which can go to the heart. Once it does that, it gives off low energy gamma rays, and not enough hopefully to do harm to you, but enough to be detected so you can see exactly where it's going. The nuclear reaction that the technetium's undergoing is gamma radiation, shown here. Here it is, just that should be a 43 right there. That's a typo. But it just gives off gamma radiation. Since it only has a half-life of 6 hours, you can't just store it that way. It's typically stored in the form of molybdenum-42, which then undergoes looks like that is beta particle, beta emission to give technetium-43, and then now you have that, and you can use that for your investigation. But you better do it quickly because that low half-life. This can be good for any kind of soft tissue studies, whereas X-ray won't work in that region. And some advantages of using this substance is that it has a nice short half-life, so it doesn't stick around too long. That's good. It's a low-energy gamma emitter, so it can be detected using a gamma detector. It can easily form regio-specific complexes going to wherever you want it to go. And you can transport it as a more stable substance so that you can use it when you need it. Another nuclear imaging technique is a PET scanning. This is simply for imaging, not for treatment. These can use, for example, fluorine-18 compounds. So that's your radionuclide there. Here's an example of one. There's your radionuclide attached to a glucose molecule. So this is fluorodeoxyglucose. Nice delivery system. This undergoes positron emission, which is shown here. Notice they were eliminating a positron. This is an electron with the wrong charge. What's really happening is the neutron is turning into a proton and it's forming an electron, and that signifies that. And that's the process that positron emission can be detected, and it can be used for tumor visualization. Don't really be led to believe this is tumor treatment. It's just for visualization. So the F18 can be seen systemically, but it also can be seen accumulating in cancer cells, so it's a good visualization technique. MRI is far more common and far safer. It's another imaging technique. It does not include a radionuclide, but it's similar in that it does involve relaxation of nuclei as they spin, giving rise to a signal. So don't be fooled. This is really not a nuclear technique, but we threw it in anyhow. There is no nuclear reaction that's taking place, and the nice thing about it compared to X-ray, which is historically the go-to method, is that it's good for soft tissue. Most people are pretty familiar with magnetic resonance imaging. Some advantages is that it relies on the same principles as nuclear magnetic resonance, which as a chemist I'm familiar with, meaning that it can map all the hydrogen atoms in your body, and it's a non-hazardous technique. Radiotherapy is used extensively for cancer treatment. This is an external technique here. Common radionuclide is cobalt-60, which is a gamma emitter, a high-energy gamma emitter, so it's that energy that is used to target cancerous regions. Here's the gamma emission here. This is actually, when you look at that, that is the gamma emission as a result of a beta particle forming. And there it is. See how the math always works out? Atomic number, mass number, and there you go. This can be used for solid tumor treatment. However, more insidious, unfortunately, are the non-solid tumors, things like leukemia. They can go all over the place. It would be difficult to target all those individual substances in your bloodstream, right? And so for that, an approach that's in the experimental phases is targeted alpha therapy, where this can be an internal radiotherapy technique. So you don't have it just like zapping you from the outside, you bring it inside. The idea is you take a radionuclide, for example, lead-212, and you bind it to antibodies which go to cancerous cells. I hope you can appreciate really the brilliance of that kind of approach. Sometimes referred to as a warhead approach. That means that once it's in your system, it will bind to cancerous regions all over your body and then target them individually. This is an alpha emitter. Alpha emitters look like this. Notice the math here. There's your alpha particle, helium-2+. And they are good for non-solid tumors because that alpha emission is of high energy and of short range, so it can go to different individual spots in your body simultaneously without harming other spots. And you perhaps can think of it as targeted bomblets. So once it goes into your system, separates out, and each one seeks out a cancerous region. The promise sounds great. I don't know what exactly the status is clinically, but this is a good example of a targeted approach. Okay, this is an introduction to nuclear imaging and radiotherapy.